Okay, now we got to get through the rest of this section where we're going to talk about what's called formal charge, and then we also are going to talk about the geometry. Okay, some of the geometry things. Now, what formal charge helps us do is it helps us compare various Lewis structures and figure out which one is the best. And this is an add-on. We did not do this last year. And pretty much the way that functional charge works is you take the number of valence electrons, which you get off the periodic table, same way we've done it. We take that and we subtract the electrons assigned to that atom. Now, how do we assign atoms, or electrons rather? Well, they get credit for all of the lone pairs, and they get credit for half of the bonding. So we essentially take those bonds and split them in half and just kind of assign them. Again, this is a model. It's not perfect, but it gives us one more way to try to compare these things. Again, the valence comes from the periodic table. All right. So remember, this is not real, but it provides less extreme charges than oxidation numbers, and the whole goal is to figure out which Lewis structure are we going to need. Now, the sum of the formal charge on the molecule must equal the overall charge on the molecule. And so we'll get there, okay? And the goal is to get atoms to a formal charge of 0. That is the ultimate goal for this. And this is how we're going to pick which Lewis structure is, that which one gets us closer to 0. And any negative formal charge must be on the most electronegative atom. So again, we come back to this idea of electronegativity, where we've got fluorine, oxygen, nitrogen, and chlorine are really our most common electronegative elements. Okay, so again, some other rules. Long pairs belong exclusively. Shared electrons are divided. I realize some of them are repeats, but I just want to really emphasize this stuff. Formal charge closest to 0. Negative formal charge is on the most electronegative element. Okay, so let's look at sulfate. We know sulfate has a 2-, so it's going to have 32 total electrons. Now, here are two possible versions for the sulfate ion. I'm guessing most of us probably would have gone with this one, but this one can work too. It meets the rules, except for the fact that it went right to a double bond. Now, one thing, we would put brackets around it for 2-, but that's just a housekeeping thing. Okay, so let's look at formal charges. Well, if we look at sulfur, sulfur gets +2. Why did sulfur get +2? Well, if you look on the periodic table, sulfur has, I'll do this up here, valence electrons of 6 valence electrons. Okay, it has 4 assigned to it. 1, 2, 3, 4, because it gets credit for one of each of those bondings. So therefore sulfur is going to be +2. Now each oxygen is -1. Why? Well, oxygen is going to have 6 valence electrons, and it gets credit. Each one gets credit for 1, 2, 3, 4, 5, 6, 7. So 6 - 7 is equal to a -1. And that's this formal charge. Now when we come over here to this one, here are the formal charges. Well, if we look at sulfur down below, all right, you can have, it's got 6 minus 1, 2, 3, 4, 5, 6. Okay, equals 0. And then oxygen we already did, but if you look at this oxygen now, it gets credit for 1, 2, 3, 4, 5, 6. So 6 minus 6 is equal to 0. And so when we look at which one is favored, it's actually going to be the one on the right, simply because the formal charges are the lowest. Okay, so sulfur is 0, and we also get the oxygens equal to 0. And same thing, overall we get a formal charge, total formal charge equal to -2, which is what the molecule. So it's closer to that. Now, before you panic and you go, oh my gosh, what if I don't know there's 2 options? What if I draw 1? You got to pay attention to how the question is worded. If the question said write a Lewis dot structure for sulfate, and you drew this meets the rules, and I would give you credit for it, and you get full credit. If it said provide 2 structures for sulfate and pick which one is better, that's your cue that there's more than one option, and you've got to provide formal charges. Don't panic on that just yet. Okay, N2O, you've got dinitrogen monoxide. These next couple I'm just kind of go through a little bit faster because I'm sure we'll talk about some in class. There's 16 total electrons. There are actually 6 different options, and this is just to show you some of those really ugly combinations as to why we would pick. You know, there's 6 different options, and again, nitrogen gets a +1 here because when you look at nitrogen on the periodic table, it has 5 valence electrons. It gets credit for 1, 2, 3, 4 here, so it equals to +1. That's just where that formal charge came from. Now I've already done all the math for you here, but if you look at it, this is going to be the most favorable combination. Why? Well, the big difference is right here, is that nitrogen, this is the lowest formal charge than any of them have. Okay, so it's +1. It's the lowest formal charge of any of the central. Now this one, these two also have +1. Okay, so that's going to rule out all of those because we don't want +2 in the middle. How do I differentiate between this one and these two? Well, if you look over here, remember oxygen is the most electronegative element of these, and this one has the -1 attached to the oxygen. So that's why this one had oxygen at 0, this one had oxygen at 0. Okay, and so that's why this is going to be our more favorable one. Okay, again, if it just said write a structure and this followed the rules, you'd be okay. It's when it says indicate formal charge, you got to think that next level. Nitrogen dioxide, again, here are the two options with formal charges. You know, where do we get nitrogen equal to 0? Well, nitrogen has 5 valence electrons. It gets credit for 1, 2, 3, 4, 5. So it equals 0. Oxygen has 6 valence electrons. It gets credit for 1, 2, 3, 4, 5, 6. It's equal to 0. All the zeros, this is the one that is favorable. Okay. Excuse me. And this also would be a resonance. No, I'm sorry. Yeah, it could be a resonance structure as well. But this is the more favorable one. Okay, and I know you're looking over here going 1, 2, 3, 4, 5, 6. How come there's one not paired? I get that. This would be one where if it was given, if both of these structures were given to you, like you already had it, you didn't have to come up with them, could you justify why this one would match? Because I know that doesn't follow the rules, I get that, but this would be one where you were given both structures and explain which one was more favorable, so you wouldn't have to just come up with one extra lone pair up there. I'm sorry, one unpaired electron. Carbon dioxide, here's two versions. This one has 2 double bonds. This one has a triple bond and a double bond, which again, carbon has 8, so it's happy. Oxygen has 8. So the way we tell the difference is we go to formal charges. Carbon is 4 minus 4 here. 1, 2, 3, 4. Each oxygen is 6 minus 6. So that's why we like this one better. Thiocyanate ion, little review of our ions there. A couple different versions that we could have. If we look at all 3 of these, they all have carbon as 0, so that's not going to rule it out. But the reason we like this one better, here comes my little circle, is that nitrogen is the most electronegative element. Okay, most electronegative element, so that is why this one is favored as compared to the other 2. Okay? Just when we thought we were doing okay. All right, perchlorate ion has 32 electrons. Okay, here are a couple of options. The one on the left would be favored because it has the lower formal charge. Again, if it just said to write a Lewis dot structure and you wrote this one, you know, I would give you credit. You got to look at the way that it's worded. If it talks about the best structure and assigning formal charges, that's your mental note that, okay, something else is out there, and it all comes down to having the lowest energy and making those atoms the happiest that they can be. And again, it's a model, it's not perfect. All right, last thing we got to talk about is VSEPR theory and molecular shapes and geometry. VSEPR theory stands for valence shell electron pair repulsion. Okay, this part is huge. We need to understand the background a little bit more than last year. Last year it was just memorize the shapes. The repulsion between the pairs of electrons around an atom cause them to be as far apart from each other as possible. And this is where we're going to get into the bond angle, and we got to be able to explain it a little bit more, and you'll see this a lot of times in the essay questions, and it's used to predict the geometry of molecules. Now I gave you a chart that I'm going to refer to at the end that's a little bit larger than the one last time, so you may want to go ahead and take that out. Little bit of going through the shapes. Diatomic molecules will always be linear, and all other molecules can have different shapes based on the steric number of the central atom. Now don't get thrown by that term. Steric number is just going to refer to the total number of things coming off of the center, and that's going to be including bonding pairs and lone pairs. And depending on the number of them, that's going to dictate your shape, so you may want to start memorizing them. Here are the big ones we had last year. If you only have 2 lone pairs, it's linear. 3 lone pairs, trigonal planar. 4 tetrahedral, 5 trigonal bipyramidal, and 6 octahedral. Okay, and it's just talking about that. Remember, when we do geometry, we have to talk about the perspective of one atom. Usually it's a central atom. Sometimes you can have more than one geometry based on different things, and we'll try to get out the models and build some of these so that we can see them as well. Alright, now a couple of tips. Draw the Lewis structure, find the parent geometry, picture without the lone pairs to get the molecular shape if you want to. The lone pairs will take up more space than the bonding pairs because of the repulsion. Okay, that's the big ticket one on there. Treat all bonds the same, meaning that a double or triple, it does not matter. It still only counts as one bonding group. Okay, one bonding group. So if we look at, for example, up here, this is kind of one of those ugly ones. You've got xenon. Now when you see these balloons up here, if you draw the Lewis dot structure for xenon, you actually find out it's one of those that exceeds the octet. This is just showing you that you have a p orbital that's got some electrons floating around up there. And what happens is they want to get as far apart from each other as possible. And so that's where it leads to this structure where you're still going to have these two up here. Okay, and again, we'll go through this more in class too. Steric number 2, if there's no lone pairs, steric number just means off of that central carbon, there's two things coming off of it. Okay, if they're both bonds, it's going to be linear. The steric number is 3. Kind of blowing through this because we're going to do a lot of this in class. If there's no lone pairs, it's trigonal planar. Again, we do need to know the bond angles as well. You can refer to the chart that I gave you for those, and we'll mention these in class. And this is the real life version because those bond angles are all going to be 120 degrees. Okay, this is not necessarily drawn to scale because they get as far apart from each other as possible. Now, if it's got a lone pair and two bonding groups, it's bent. Okay, and again, this is the real world version because that lone pair is going to push those bonding groups away from that central atom. And again, doesn't matter if it's, this kind of shows one double and one single, we treat the bonds as being the same. Okay, steric number 4, if there's no lone pairs, it's tetrahedral. So that would be our methane molecule. Remember, the bond angle here is going to be 109.5. We'll build some of these in class to show you. It's not going to be the 90 degrees like it looks like. Two lone pairs, you get water, you get bent. The reality of it is that these two lone pairs are up here, and they push those bonds down. Okay. And this is just the way it shows up. They don't end up on the opposite side, and it has to do with the P's and the overlapping stuff. But one lone pair, ammonia, would look like this. It's going to be trigonal pyramidal. We learned all of these last year. And again, that lone pair up here pushes those bonds a little bit closer together. This is just showing you, here you've got with the bent, it's kind of like Mickey Mouse. This one's kind of going straight up, this one's kind of coming at you. And we're going to draw 3D versions a little bit different than we did last year. And if you see me draw like a triangle like this, it's coming at you this way. And we'll do more of this in class. Alright. Bond angles, again, here's your methane, which is 109.5, your ammonia, which is 107, and your water, which is 104.5, because the two lone pairs out here push those together, and the one lone pair push those together, then no lone pairs with methane. Okay, steric number 5. This is the one we learned last year, no lone pairs, trigonal bipyramidal. Here's the AP version, is that if you can have lone pairs in these, if you have SF4, where there's one lone pair and 4 bonding groups for a total of 5, that's going to be what's called a seesaw. And when you see the 3D version of this, you're going to understand where the seesaw version comes from, because I realize that does not look like a seesaw right now. But this is the 3D version because it kind of settles out. It almost looks like there's a spot for the legs of the seesaw, and then they're flat, and then the lone pair would be up top here. Okay, and again, we're going to build these in class. We're going to take a whole lab to do this. Alright, steric number 5, we had 2 lone pairs and 3 bonding groups. So we've got 2, no, I don't want to do that. Go away. Okay, we've got 2 lone pairs and 3 bonding groups. This one is going to be what's called T-shaped because this is what it drives it. And we saw this, or this would be